Hello, everyone. A very good morning to everybody present here. I hope you all are doing great. My name is Srishti Vadhera, and I will be your host for this session. I welcome you all to the day one of pre hackathon speaker sessions at hackCBS 3.0. Continuing the legacy of our seniors with much pride and honor, we take the privilege to organize the third edition of hackCBS, which is India's largest student run hackathon. Making full use of this digital time zone this year at hackCBS 3.0, we will be hosting lots of live workshops and speaker sessions throughout this week. To know the detailed schedule, you can even check out our website. Thus, we hope to make it a memorable and insightful experience for you all. So let us begin with our much awaited sessions. Now, talking about today's session, this session will cover in detail knowledge of how a PostgreSQL database can be scaled to support a monthly inflow of 10 plus million data points and serve it over a REST API with an average response time under approximately 90 milliseconds. With that being said, let me introduce you all to the speaker of this session, Sambhav Jain. So here we have Sambhav joining us. Sambhav is a software engineer at Xencov. Sambhav is highly proficient in JavaScript, Node, React, Bootstrap, and many more. He's skilled in C++, Git, and OCR as well. We welcome you, Sambhav, and look forward to your talk. The virtual stage is all yours.
Hello everyone, this is Sambhav joining you. So I hope you guys are will enjoy this. I hope all of you are healthy. All right. So this session will mostly cover how to scale a PostgreSQL database. So PostgreSQL is basically like a counterpart or a sister like database system to MySQL. I think many of you might have used it. I'm not sure. So there are like these nitty gritties in Postgres that differ with MySQL, but we won't cover that in this session. This will cover that how, in my personal experience, uh, the database performance was improved by 25x by just employing a simple indexing strategy. So, so let me start. So this is my introduction. I'm Sambhav Jain. I'm a software engineer at Xencov. I work in their full stack team. So, as I said earlier, this will cover indexing and other optimization strategies one can perhaps employ to make a database faster, so that the queries, like the response times, could be better. So that's about it. So a little bit background in uh, what the how I came up to this point. So we all know that it's really hard to manage a database, right? You have to manage the keys, foreign keys, primary keys, and all those things, right? So and when the expanse of data becomes large, say there are like 200 million entries at a point, so it will be really difficult to manage it then. And then how to keep it streamlined and safe and reliable, and all those things like the asset properties you might have heard that go with DBMS, any DBMS system. So not so long ago, I was building and leading the development of a tray, basically this thing where we aggregated like international import export trade records. So it had to be really fast, like blazing fast. The responses had to be like served within seconds. So like in the beginning it was like it's okay, it's like there was a little to nothing in the database, so it was like okay, the database is doing great. But subsequently afterwards, when we like pushed like 200 million or so entries, it became very slow. Like it usually responded after like say 5 to 6 minutes for simple queries, not so much. So so uh, when we came to that point, we realized that perhaps we should employ a better indexing strategy. Earlier one was very simple, the default one that comes with any database. So the big problem. So what is the big problem in scaling any database system, right? So the big problem is really not knowing how to improve the database performance, right? So be like Dwight Schrute, you are like, how do I do this? So it's really about choosing the right optimization strategies, right? So there could be you can employ multiple optimization strategies in conjunction or separately. It doesn't really matter, but uh, it matters. The first thing you should ask is, should you optimize the database? So the answer to that is like, if the database is going to needs to be fast, needs to store a lot of data, so you should perhaps use any kind of optimization strategy that is available to your own case, to your own database. So in context of PostgreSQL, what we can use is indexing, partitioning, sharding, using copy commands to insert data, and reducing relationships between tables, and then custom server configs. So I will cover indexing in detail in this session, but rest of this I will explain in brief here. So partitioning and sharding are two things that are very similar to each other, and people like uh, treat them in the same way. They're like they are like synonyms, you might say. So partitioning is nothing but dividing the database in a way that it optimizes the queries. So say if I have a database, so it has like 40 columns, so 40 properties, and then there are like 60,000 rows. So I can now partition it in two ways. I can like horizontally partition it, like I keep every column, but I divide the number of rows for each partition. So maybe I made one fourth of each, so like 15,000 rows, and the column count is still 40. So that is one thing. There could be vertical partitioning where I divide the table in columns. So say I divided the columns in one fourth, but I kept the row count same. So there are like 60,000 rows of 15 columns. So like that. So basically sharding is like a subset of partitioning. So we do the same thing. The applications are same, but in sharding we employ the same things over a master slave kind of network, where there are these load balancers and there are multiple servers. So we can shard a database and uh, keep that separated from other shards. So basically, say if I have a database in a master server, so I sharded it and then saved the sharded uh, smaller databases to these slave servers. So then subsequently, when the master comes back on, say it went off, so I can like send the data back using this. So another thing could be to use a copy command. So copy command is basically nothing but say if I have a CSV file, right? So it has all the data in the right format. I don't need to pre-process it or anything. I just need to insert it. So there are two ways to do that. You can either go row by row, you can insert every row individually, or you can just copy the whole damn thing at once. So doing it row by row can exhaust the memory available to your server and crash it. So that's what happened in my case. So we then used copy command. So there could be a file, say 500 MB. It has like 10 million rows or along those lines. So copy is basically from copies basically it just takes a file as an input. It takes what columns to push. It just copies the data directly to a database from the file. So so basically, like in JavaScript you have these console log statements, right? So we call any kind of logging is basically interacting towards you, so towards us, the users, right? So that is std out. So sending any data back in, like using prompt in JavaScript to give some input. It's stdin. So forgive me. So so that's about copy command. And then relationships. So relationships is one thing that we tend to reduce in our job as well. So uh, as long as you have less and less relationship with those with that table where the data is going to be huge. So like I have this subscription table, there is a user table, and there is this data table. So and I might have relation to both user and subscription, but the data table could be like having 200 entries. So the management of those foreign keys will become really difficult, and the queries will become slower. So relationships should be kept minimal. Custom server config is nothing but setting some settings, tweaking some settings in the right way, so the um, server optimizes the queries a bit by itself. So let's move to indexing. So what is indexing? So indexing is nothing but a strategy, as told before, to make database queries faster. Uh, so basically what it does is, what the gist is, we, like any kind of data structure being used, uh, database is basically built on data structures, right? So it will use storage, your local storage or maybe server storage. So there will be disk accesses. You It's called a page. The Where the data is stored in postgres, it's called a page. So the data would be read from a page and then to via a particular orm to your server, or and then you will send the response back. So indexing is nothing but to minimize these page accesses but after subsequent calls. So basically this is like, if I'm making the same call on maybe different parameters but the same call, and the queries will span across the same table, not differentiating very much, so then I can just employ a particular indexing strategy, a particular kind of indexing type. So that will this is like a trade off in storage versus time. So if you can sacrifice some storage, you should use indexing, as this will be a data structure in itself and will be stored in the data in your database only. So there is this trade off that either you can keep the storage or either the time could be lowered. So the storage is a secondary thing in most production environments, so we prefer time always. So they are basically attached to the to the tables, right? So the to the data, to the properties, the columns, whatever you call it, whatever the context be. So they are just a auxiliary kind of data structure which basically refer to the original location of the data. So I'll show you how a basic index representation is in a bit. uh, but like I said before, there is this correlation between optimizing this data structure as much as possible to make the queries faster. But please keep in mind that indexing, any kind of indexing, should be done in a right way. You, like, say there are 40 columns, right? So if you want to do indexing, uh, come up with some subset of these columns that we use very often from any API, it doesn't matter which. So we can't put indexing to all 40, as that will just destroy. Like, employing indexes on the whole table has no meaning. All right. So that will not make the queries faster. So you have to pick a subset of columns that will be used upon on a regular basis. So only those columns will have an index, and only those columns will serve the queries faster. So as said before, like any other data structure, they will occupy some space in the database itself, attached to the table or the columns they are being attached to. So this is a simple structure of index in a database. So we have a key and a data reference. So if any of you guys know about pointers in context of any low level programming language like C++, I might say. So in pointers as such, we have a similar thing where I can set a pointer to a value at I can set a pointer to a value in to a variable basically in a program, and that variable will be stored in the memory, right? So I have set a pointer to a memory object. So uh, I can just use the pointer to refer to it from onwards, so I don't have to use the variable itself to get the value. I can just use the pointer, right? So there is a similar thing. I have a key which I can make on my own or the database will, and I have a reference. So the reference here will be, it could be a page number in the database storage to refer to the actual thing. So to to basically access the value itself, we will need to have the key, the search key. So we will need to have this. So in context of PostgreSQL, there are these kinds of core types under the hood that they use. So B tree, hash, gist, and gin. So by default, B tree indexes are implemented. So what is B tree and hash? So B tree is nothing but a balanced tree where these are leaves, right? So these are these leaves node. Just a second. The last portion of this tree is called a leaf section. So if every leaf node here is on the same level, it's a balanced tree, right? So it doesn't matter if this has like 2 and this has 3 and this has 1. All of these leaves will need to be on the same level to be balanced. So basically this is like this thing where uh, values are balanced, right? So there is this metadata, so that doesn't matter much. But uh, say I have to search for a value, right? I have to search for a value within this. Say I have to search for 49 as shown here. So I go to this is my uh, top key. So it has references to say 4, 32, and 64. So basically you can treat these as keys, and then uh, whatever these point to internally, that doesn't matter much for now. So maybe the key, maybe I needed to search for 49, key number 49, right? So I search for 32. So then I see where should I go. I see I should go to the lower part, the 43. Then I subsequently go to 48 and then 49. So then I can just uh, get the data back. So uh, the data will be in the sorted order. Only comparison type operations are permitted, like greater than, smaller than, greater than, equal to, smaller than, equal to, and it will be a bit slower as compared to hashing. So hash index is basically one kind of indexing where we use a hash table. So the pointer references themselves are used uh, are the pointer references are stored in a basically hash table. The hashing function uses the search key. So I can just pass the search key to the hash function, and that will just spit out the appropriate location of the pointer to the actual variable being referenced. So since hashing is always faster compared to any other kind of data structure, as it is like direct access thing, so it will be a bit faster than compared to B tree, as we will need to traverse the tree a bit and then maybe not find it at all. So there will be some kind of surety in using hashing hash indexes over B tree indexes. So here only equality type operations are permitted, as hashing is based on equality by itself in its nature. So all right, so next is gist and gin. So gist is basically one kind of indexing where we will need to where we might have, say, just a geospatial data, like the location data of a continent or a country, or the school data of something, school data of some country or some state. So we, where the expands in the type of data is uncontrollable, like we can't limit to, say, character, variable type, or uh, date type, or number type. So in those scenarios we will need to use gist indexing. So basically in this diagram, say I have to search for 55 and 60. Basically this is a searching in range, you can say. So I need to know for all elements that are in these range. So these ranges are basically keys to the values being referred. So I check where in which interval of these this range comes in. Then this is between 1 to 200. Then I go to whatever the packet is being referred by 1 to 200, and then I select the appropriate value. So these values are the actual values from some kind of geospatial data. So in Postgres uh, we can use a extension called PostGIS. So PostGIS is nothing but extension to Postgres to use this kind of data, this kind of geospatial data, where the data is irregular, the types are irregular, and the applications are vast, and the times are, of course, the response times need to be as low as possible. So that's about gist. Next is gin indexing. So say I have some, all right. So in both gist and gin, we might use in a simpler database as well, but the base context is that uh, they use a search called full text search. So full text search is something like if I have to search across multiple, not across multiple tables, but across multiple columns, and I'm not specifying which column is what, I just give a value. So if I have either one of these, gist or gin, I can do a full text search. So full text search is like this. So I have a search value, say Sambhav, right? So it makes anagrams from this text portion. So it will search for S, it will search for SAM, it will search for BHAV, just like that. So, and this could be a part of a bigger string like Sambhav Jain or Jan Sambhav, something of these, something of this sort. So in that kind of application, the full text search comes into play. If you, any of you guys have used Algolia or Elasticsearch, so those guys use full text search. It's a similar concept, but not in this context currently. So coming to gin indexing, so if I have, say, array like values, so array like properties, there is a lot of data, and I have to search across the array. The data is just not a single bit, it's not atomic, right? So in this diagram, so a bit background in what this meta page is like. As before, there was this meta thing here, the meta thing here. So meta is nothing but metadata to table, right? So metadata could be like when it was created, how much data it has, what size it has, where the pointer location starts in the storage, where it ends. So how many relationships are there, so primary keys, foreign keys, that is basically the metadata. So it's a bit different. So in a very brief, it's like multiple b trees. Every index has a b tree in itself. So like, say, in b tree there were like values, reference to values, right? So in gin there are reference to b trees, and those b trees have values. the array like values. So it's a little bit difficult to understand, but it is what it is. It's like it says I said, uh, indexing reference to b trees, and the whole thing is in itself is a b tree. So b tree inside b tree. The inner b trees are called here posting tree, and the outer tree is called entry tree. So there are these multiple things in Gen indexing, like this fast update list in orange below. So fast update list is all right. So in Gen indexing, the data insertion is slower, right? The index management becomes a bit slower as you like insert more and more data, but the retrieval is very fast. So fast update is a context is a concept in Gen by their creators. So where the updates could be made really fast. The updates like edit, create, whatever, post or put request, right? So those kinds of thing can be made fast. So that's really when this fast update list comes into play. So out of context for here. So I think let's move on. So how do we create a Gen index, right? So we have these statements. These statements will be executed in a Postgres terminal. So either could be a local server or a remote server, doesn't really matter. But let's go over the lines. So first is create extension pg underscore trgm. So create extension is the thing where like some things are not built into Postgres by default. You have to like they are there, but they are not activated, or they are not like attached to Postgres right now. So create extension xyz does what it does is it attaches the xyz extension to Postgres. So subsequently I can use that technique, that technology inside my Postgres database. So here pgtrgm means a trigram. So trigram is again the same thing as told before. It's used to employ the full text searches. So in a very basic way, it will just make anagrams of the query text you have sent, and then use the appropriate indexing strategy you have used internally to get the values. So the second statement is to create a Gen index itself. So normally we just write, we could have written create index and nothing here, the and then index name and then table name and nothing here, nothing here, and then column name. So that could have done the part, but here this is the syntax to create a Gen index. So it is what it is. So this is an example of one of our production databases where we have used Gen indexing. So here you can see there are these indexes with uh, pk in pk prepended to every index. So pk is nothing but primary key. So by default what Postgres does is when you when you define a primary key has to be unique. Any kind of primary key has to be unique, and to maintain its uniqueness, Postgres creates an index of that primary key, so that subsequently whenever a new data has to be inserted, it will just search for the last uh, key value and then give a new one to it. So there are these tables, many tables, so every one of them has a primary key, and then there are these two kind of table called import data, export data. So they have so many indexes, right? So why? So basically, and not every column is has a index, right? So there are like multiple index. There are some b tree index, right, like here, and there is a b tree index here as well. So basically the gist is that we can use both B-tree indexing and gin indexing, but apply B-tree indexing to those that are less frequently retrieved as compared to those columns that are more frequently retrieved. So in our case, there were these values like exporter name and FOB and foreign port. So all these values were being retrieved very often. So you can attach a gin index to it, and then it will make uh, that column really fast. So moving on, this is our observation from our usage of gin index. So while we were having like 35 seconds, we were waiting for 35 seconds to get a response, to basically download a response, I can say, uh, on the web part. So that is now under 2 seconds. So it's really great to see this, but it's really effective, right? So the gene indexing in itself is really effective because of the data structure and the algorithmic implementation the guys at Postgres have done. So moving on, these are some additional resources for you guys if in case you get a hand on this presentation. So some blogs, videos, articles, and things. So I think that's about it. I say thank you. And if you have any questions, please let us know.
Indeed, a very insightful session. Hope the audience agrees with me. Thank you, Sambhav, for enlightening us with your knowledge. It was really good to seek all the information from you. Now, we shall proceed towards the questions from our enthusiastic audience. So, go ahead with your questions, dear audience, and we shall entertain them one by one. I think people are thinking of their questions. So, till then, Sambhav, can you please give some advice to our hackers since there's going to be a hackathon as well in this week only. So, would you like to give some advice or suggestions to the hackers?
Um, I think hackathon in itself, it doesn't need much to be suggested by anyone, but it's like this thing where people come, they experience the nitty gritties of collaborating with other people, meeting other people, and then maybe create something beautiful in the time they have been there. So I myself have been to 3 hackathons. Two of them were hackCBS, so one of them was something else. So it's really experience to know. So even if you are not building anything, it doesn't really matter much, but the experience in itself is a big takeaway. So you can meet people, there are like these sponsors you can meet, you can talk to them, understand what they are building, understand others people's problem statements they are tackling. So basically get a gist of what is happening in the industry, and then network a bit, establish a network, create connections with people. So that will go up, uh, that will go along with you in your career, as these connections matter a lot. So and moreover, if you can build anything, it's really nice. uh, Maybe it can turn into a startup and you can win prize here as well. It doesn't really matter. The participation is really big thing. If you're participating, it's nice. If you are collaborating, it's great. And if you're networking with others, it's really beautiful. So I think that's about it.
Truly said Sambhav. So, here we have a question from the Nomad. Is PostgreSQL better or MongoDB?
Okay, so hello, the Nomad. So it really depends on what your application demands, right? So they are two different kind of databases. In MongoDB, we have JSON like storage mechanism where the data is records are basically stored in JSON like format. So it's really easy to understand and and then debug anything as compared to a SQL or SQL kind of database like Postgres in my context. So both can be fast, right? But if you need to be like very fast, like the downtimes have to be low, the response times have to be low, there should be minimal idle time in downloading the request and then getting the request perhaps. So I would say Postgres is better, but there would be a learning curve in Postgres as compared to MongoDB. So if you are a beginner, I would say MongoDB would be better. But if you are experienced, you have some knowledge of internal database structures and perhaps have built some applications with MongoDB, then you can maybe migrate to Postgres and then use it in whatever environment you are working in.
Okay. So next we have a question from Akshay Sharma. What
All
purpose does PG add in
right.
PostgreSQL Server?
Right, right. So, hello Akshay. So, PG admin is like this PHP. You have this PHP admin, PHP my admin, and PHP server, right? So, it's like this thing where you can create and manage the databases, the local databases you have. So, basically, it provides a GUI to everything you need to know about your databases. Uh, so most people use it in their local environment, as the server part would take a lot of time to host. So yeah,
Okay. So we have next question from Jatin. Any tips to enhance security while working with Postgres?
hello Jatin. So I think securing a database is not really something people look at. So you should secure the APIs really. You should secure the servers and then the APIs and then maybe the database. I don't know if you can secure a database, but you can very well secure an API and a server. So securing an API would be better. Say you can attach some middlewares which will check for cookies and tokens and then uh, reject the response if it's unauthorized and then listen for maybe DOS attacks. Many people making calls at the same time to crash your server. So those things can be managed on the server itself, on the server and API layer itself. But in terms of database security, I don't think you would need to worry about that much.
Okay. So I think the questions have been asked by the audience. Thanks once again, Sambhav. It was a wonderful session and it was amazing hosting you today. Thank you so much.
Yeah, Shishti, same to you. Have a great day. Bye.
Thanks. So I would like to thanks to our very patient audience too. So we are having our next workshop at 3 p.m. today itself on machine learning by Arsh Goel. So do set up your alarms for that workshop too. Hope to see you there. Till then, take care. Bye.